In this video, I'm going to show you another example from chapter 2. We're going to see how we can use the define data type tool to help us build a data structure called abstract syntax tree. So it's an example that it's about interface for recursively defined data structures. So this is last example in the chapter. So recall that in the previous video, we look at the defined data type. So it's a domain-specific language for defining this interface, abstract interface to a data type in terms of a set of constructors and other functions, extractors or predicates. So we use the occurs free as example. So occurs free is this kind of function that takes a procedure that takes a symbol and lambda calculus expression and give us a Boolean value, right? So we are able to use define data type to define this interface conveniently, so we don't have to come up with all the procedures, but there's a syntax, there's a pattern we have to follow, and then this keeps our program really clean and easy to read. Okay, so now we're going to review the abstract lambda calculus expression, and we're going to see how we can take some concrete syntax code that follows the syntax and turn it into an abstract syntax tree, which is a data structure, a recursively defined data structure, and we're going to use the defined data type to represent it. So here is the example. So in the end, we want to be able to represent this kind of code as an internal data structure. So this is quoted. So this is like a program, right? So this is like a stream of letters, a stream of letters, and then in the lambda calculus syntax, here's the grammar. So in the lambda calculus syntax, everything is a lambda calculus expression, but it can be one of the three kinds. It can be identifier, so it's just a symbol, it represents a variable. It can be a lambda expression that follows this concrete syntax, which means we have to have parentheses, and the first element needs to be this keyword lambda. And then in parentheses, we have one identifier, which is defined here. So any symbol. And then the body can be any lambda calculus expression, which means it can be an identifier, a lambda, or an application expression like this. So application expression basically means in parentheses, we have two lambda expressions side by side. And then the first lambda expression, it's better to be something applicable, right? So a lambda, for example. So this is a syntax inductively defined using this grammar. What to represent a program in this syntax, we need to come up with an abstract, a structure, a data type, a data structure to represent recursively, a recursive data structure to represent this kind of recursive program. So on the bottom, this line, this is our called abstract syntax. So we're going to take the concrete thing and decide how to represent it. So for example, for identifier, we're going to use something called a variable expression. And then the only thing we need to remember is the name of the variable or the identifier. And then for lambda, we're going to use lambda expression. So this is a tag, this is a name, and that represents what this is. But then once we know its type, the only thing we need to capture is the bound variable, which is the parameter, and the body, right? So we need two pieces of information. And then similarly for application expression, we need to remember what's the operator and what is operand, and each of which can be any lambda expression, can be a var expression, a lambda expression, or application expression. So what's on the top is the grammar for the concrete syntax, what user can type. And then on the bottom is the abstract syntax, is the construct, the interface procedures that we're going to use to represent this concrete syntax. So to differentiate the two, we call it abstract syntax. So it's really the essentials that we need to know in order to interpret this kind of program. So this is the first step. Given the program source, we want to build this internal structure so that we can possibly understand what the program means, right? To evaluate the program. Okay, so that's a lot, right? We're going to look at a concrete example and draw some pictures to see what the result could look like to develop some intuitive understanding. Okay, so first we use define data type. Okay, so everything is a lambda calc expression, and then we get a predicate for free by enumerating all the possible things we can have. So we have variable expression, lambda expression, an application expression, and then we list the fields. And the validator, the predicate that can be used to validate the this field. So when we call the constructor like var expression, this identifier, this procedure going to be used to validate the input. So if a user use var express constructor but passing a invalid argument, and then we're gonna throw an error. We're gonna know it, and we can stop right there before we proceed. So for a lambda expression, we need identifier and a body, which can be any lambda calculus expression. So this is a recursively defined. Okay, so we define identifier as the same as a symbol. Okay, so here is the meat of the example. So we have a parse procedure and then onParse. So parse will take a concrete program and create abstract syntax tree using the procedures we have here. And then the onParse does the reverse. So it takes abstract syntax tree, it's going to give us the program in the concrete syntax, so we can verify the correctness of our procedure. So, okay, so I'm going to copy this whole program and put it to my editor. Run. Okay, everything looks fine. Okay, so let's see, that's how do we parse? Given a datum, okay, a piece of data, a program as a piece of data, we're gonna construct this abstract syntax tree. Well, since the abstract syntax tree is they're only in the lambda calculus expression syntax, there can only be three different things, right? So we're gonna analyze the text to parse it, right? In other words, to figure out what kind of thing it is. So let's read through the program. So given a data, if it's a symbol, if it's a scheme symbol, then it has to be a variable expression, right? So we construct this. So when we parse a datum, and then we return variable expression, because that's the abstract syntax or the internal representation of that in the form of abstract syntax. So this parse expression is a, actually, do I have it somewhere? Yeah, I don't have it, but we can define it like this, right? So given a program is going to give us a abstract syntax tree representation of the program, okay? So we use the constructor we get from the defined data type to do that, to construct that. So if it's a pair, okay, if it's looks like a list, right? Remember, a list is always a pair. Actually, I have a graph for that, a picture for that. So so a list is consists of a sequence of pairs, right? So if you ask scheme, is the list a pair? Well, it is a pair, right? It has two parts, car and curter, but if you follow the backbone, it always ends with an empty list, right? That's a proper list. So a list, by definition, is a pair. Has to be a pair, has to start with a pair. Okay, so if it's a pair, okay, let's try this. Pair is a built-in procedure that tests, so it's list. So a list is a pair. If we see, okay, we're gonna build a pair, cons, so that's gonna be true as well, right? So if we see a program that looks like this, start with a comma, then scheme is gonna think this is a pair because it's a list. So if it's a pair, and then the car of the list, the first element is a lambda, is this symbol, then we know it must be a lambda expression. So here we have assumption. We assume whatever user enter here is a representation, a textual representation of a valid lambda calculus expression, right? So if it's a lambda, then we use constructor to construct this to construct this internal representation for this whole expression, this datum, okay? And we know the car of the curder, the car of the curder, which is the second, this, right? It's the car of the curder of the curder. No, the car of the curder. Okay, let's actually do this. I'm gonna kind of dissect this for you. So, okay, just review. If we're passing this list and the car of that is this lambda, right? Okay, so the car of the curder is going to be the second element, which is that. But what we want is actually the first element of that. So we put a car there that gives us that, right? So if we're looking at the lambda expression in the concrete syntax in the program, then the car of the curder is going to be that bound variable, the parameter, right? So it needs to be identifier. So we use the constructor, and then the first field needs to be identifier. Also, whatever is in that position. So we use that to get that, and then we call the constructor with the first parameter. Then the second parameter needs to be a lambda calc expression. Okay, it needs to be a value that is in this kind of representation, right? So one of the three constructed using one of the constructors, right? So it's a parsed lambda calculus expression. So that's why we need to recursively call parse, okay? And then passing the car of the curder of the datum, which is the body expression. Okay, let's try it on this one. So if I say, okay, car of the curder, what do we get? Car of the curder. Okay, so the curder give us the remainder as a list, and the curder of that give us the remainder of the remainder. So it's going to be this as in the list, and then okay, actually let's do it one step at a time. So the curder of this is going to be that, right? The remainder of the list, right? The first is this, and then second. Okay, so now the curder of the curder is going to be all but first, right? So we get rid of that. It's still in the list, but what we want is actually the first element in the list. So that's why we're going to add another car in front of it. So that gives us that. So what this line of code says is, okay, we're going to construct this lambda expression as in a part of the abstract syntax tree, but we're going to have to parse this part, turn it into a lambda calculus expression, like a lambda calculus expression like this. Okay, one of the three. Okay, so we need to parse recursively. So in the end, we want abstract syntax tree, and in which every element is in one of the three is constructed by one of the three procedures, right? Through and through, because this is a we're turning a concrete representation to a abstract representation. Okay, so for app expression, we're gonna take the car, and then we're gonna actually recursively parse both parts, and then use that to construct the application expression. So the car and cursor combination allows us to do that. So let's actually do this. So I'm gonna take this, right? So this does look like a let's see, car of, it does look like a application expression, right, in terms of the concrete syntax. So the car of that give us the first expression. Okay, that's it, simple. To get the second one, we need to car of, okay, let's get the cursor first. Okay, let's give us the all but first in the list, but we want is the element in the list. So we need to get the first element, so we need to use the car in front of it. So that gives us that, right? So that's why when we recursively parse the two parts, we're gonna pass car of the datum to this parse expression. We use the car of the cursor, which is here, the second part, to that, okay? And then else, if neither one is true, something is wrong, so we report an error, okay? So onParse does the opposite. So let's actually do some experiments. So I'm gonna start with the simplest one. So we're gonna call parse expression. We're gonna pass in a piece of data that is in the concrete syntax, right? So this give us var expression with x, right? So this is an internal representation that may not, it's just a, we don't know what is internal, but this is a visual, the textual representation. It does make sense, right? So that's that. Now, if we have a, okay, I'm gonna do this ourselves. So what if we parse another kind of expression? So lambda with x, and inside the body is just y. So what should we get? Well, we will get a lambda, an object constructed using this constructor, right? Because it does look at lambda expression, and our parser does it recognize this and hopefully do the right thing. But then inside, we expect to see an identifier, and then a body, something that represents the body, which is itself a lambda calculus expression. And what kind of lambda calculus expression is this? Well, our parser should recognize it's a variable expression because it's a symbol of something, right? So as simple as that. So let's try that. So now what we get is we get a lambda application, a lambda expression, and we have x captured, and then we also have the body captured as a variable expression. So this is correctly parsed, right? So now I'm gonna visualize it, and this is a part of the homework. So how do we draw this? Well, we're gonna draw something. Okay, so okay. So we're gonna draw using the example in the textbook. So every object we're gonna okay, this lambda. Okay, so we have two things, right? Lambda captures a identifier, and then the body. The body has to be one of the lambda calculus expression representation using a defined data type. So we have this is called a variant, right? So this is a valid lambda calculus expression. The body needs to be another valid lambda calculus expression. So we know it should be recognized as a var expression. So I should have the exp in the end there too. So I missed that. So exp. So then this is a kind of notation with the textbook uses, right? So then this has only one field, which is y. Okay, so that's that. So this gives us this called abstract syntax tree, right? This is how we can visualize it because this is really the internal structure. We have lambda expression object with two fields. One is a identify symbol, a simple symbol. The other is another lambda calculus expression created using one of the constructors. So we use a box to represent that. So now let's look at another more complex example. So yeah, I'm gonna use this one then. So this is a, oh, actually let's try another one. So I see, what if we have just x, y? Okay, according to the concrete syntax, this does look like application expression, right? It's in parentheses, something followed by something else. But each of this part, the operator and operand, are both, should be both recognized as variable expressions, right? So now we get what we want. So overall is app expression. The first part is a variable represented by a variable expression, the second by another variable expression. So we can visualize that. So we have app expression, then in this expression we have a var expression as the operator, sorry. Okay, and then the field, which is just the variable, is x. And then the second part, the operand, is another var, var expression. And then the variable is 1. Okay, so this is the, okay, a visual representation, abstract syntax tree representation of the result we get from this expression. Okay, so now let's look at this one. This is more complex. Okay, comprehensive. So what is this? Okay, well, overall is a lambda, right? And then, but the body is looks like an application expression, right? And then this is operator, this is operand. The operand looks like another application expression, right? With the operator as a variable expression, and then the operand as another variable expression, right? So now we can see this, and you see the parentheses. This actually describes the tree. It's nested, right? We have lambda expression. The body is app expression, which is consists of a variable expression, and another app expression, which consists of variable expression, another variable expression. Okay, so this is not as easy to read, and we can draw a picture to make it more more readable. Okay, so I'm actually gonna copy. Can I copy this? We can copy. I'm gonna put the text here. Yeah, so it's here. So we're gonna draw this. Okay, so what does this look like in memory or in as a abstract syntax tree? So we have we're gonna turn this into a lambda. Okay, that's my lambda. Okay, so the first identifier is x. Okay, it's not constructed using our constructor, so we don't use the box. And then the body is an app expression. And then the app expression consists of two parts. So we have this and then that, right? So the operator is a valid lambda calculus expression. It has to be, right? So it's two expressions side by side. And then this is the first variant, the variable expression kind that represents something that we don't know yet, but this is the structure of our program. And then the identifier is f. Okay. Then the operand of this app expression is itself an app expression, right? Because it does look like app expression. So we're going to use app. Actually, we see in the output it is represented by app expression. So we call the constructor to do this. So, and then the abstract expression, so it has the two parts. Each part needs to be a valid lambda calculus, right? So the first one has to be a var, because it does look like a var, right? There are only three different possible possibilities, right? So it's a var, it's an expression, a var expression, and then the symbol is f again, and then the rand, operand, is also a var expression, and then the symbol, or the identifier is x. Okay, so this is okay. So our program parser takes something like this and turn it into this. Okay, so this is significant. This is the first step of interpreting any program. So the source code is just a piece of data, right? Has no meaning. But before we can figure out its meaning, we can interpret this program, we have to turn into a structure, internal structure that is understandable. So this clearly shows what this is, the structure of this program, right? So now, in the next step, we can just look at the structure and do the right thing, right? Recognize the different parts, what they are, and then do the right thing to them. Then hopefully we can interpret this program, right? So now, as a test, there's a onParse. So okay, so now, given a parsed lambda calc expression, we can use cases, right? This is used in combination with the defined data type, so we can turn it into the concrete syntax, right? So we list the name of the type we have defined using defined data type, and the parameter, and then we use each variant name as a case, right? So if what we see, what is given is a var expression, and we're gonna take the variable name, the identifier, and just return it. Right? The concrete representation is whatever this symbol is, right? If it's lambda expression, we'll get this will give us the first part, the bounded variable and the body. So this is positionally mapped to here. So we have these two like parameters, but this just magically take it apart, right? Extract the two parts, two fields, and then we're gonna represent it, show it or print or output it as a list, a scheme list. So what we do is we use list, we put a label there, and then we put a parenthesis around the bound variable, and then we onParse the rest of the body, right? Whatever we get, it's gonna be there. And then application, if it's application comprehension, we're gonna get the two parse operator and operand, and we're going to recursively onParse them, turn them back to concrete syntax, and put them in a list. Right? So both procedures are are recursively well defined. So basically means if we input data in the correct valid syntax, it's gonna work. It will do it recursively, and it will eventually stop. Then onParse does the reverse. So given the parsed expression, it's gonna turn it back into its original form, right? So we can verify the correctness. So this is like a round trip. So let's try that. So we have we parse, and then we define it as a P. P is a result of the parsing. Okay, this is a string representation of the abstract syntax tree we have here. Okay, so now we're gonna try the onParse to turn it back into its source form. So we take P and apply onParse, and now we get this back, so we can verify, oh indeed, hopefully, we have some evidence that the parse expression procedure and the onParse seem to work, right? We get the same thing back. So we basically take a flat representation into a structure, a abstract syntax tree, and then we take that syntax tree and turn it into this flat representation. So that's it. Thank you.